pasando un poco hacia adelante.
We have to finish a little bit earlier for two reasons. First, we have to leave the room at 12, and second, the guys from algebra might eat the cakes and coffee, so we must be faster than them. Today it will be a slightly different. I mean, probably, let's say, more speculative, because we are going to talk about. I mean, I will try to lead a discussion on a few new topics which might be quite relevant in the. Actually, they are already relevant, and some of us are starting to explore them. So. I mean, the basic idea of the group was, I mean, to get to know, etc., but especially to identify topics that might be of interest for I mean, joint opportunities for research. So this has been our journey so far, and I put this example that I put the first day. So basically, the first day. We were doing LSTMs and etc. And with an example that has been recurrent in several of the talks, we were able to. These are experiments from Victor. We were able to get pretty good accuracies before LSTMs and so on. That was as we said, a very difficult problem. Then Roy talked about transformers. And with a simple version, we already got a pretty good, I mean, a significant improvement. And then Carlos and Victor talked first, Carlos on GPT and Beta, which is a sort of stacking several transformers, basically. And once we have a sort of good pre-trained language, we can fine-tune it to do whatever we do. And that was in this same experiment with this Roberta fine-tuned. I mean, the accuracies were pretty good. And actually, Victor yesterday mentioned it. And today we're gonna basically talk about two topics which are of interest here, and several in the audience, which are Bayes and LLMs. Right? What are the opportunities and what are the problems and possibilities? And the second one was partly mentioned yesterday by Victor, which is, but we'll focus on it, which is security and LLMs, right? Which is, at least me, I'm going to concentrate on some of these topics. But before that. A little smorgasbord on LLMs, and maybe you don't know what is. Do you know what is a smorgasbord? No. That's a Nordic. I don't know the word in English. I mean, they put lots of little food and you pick, etc. So it's a Nordic word, maybe Norwegian. Norwegian. Yeah, Norwegian actually. So that's the way to have a cocktail there, and with little pieces and so on. You eat a little bit of 4 people. Right? 4 people. Right. Okay, so no, basically, as I said, if you have the opportunity, read this Chinese overview. These are some topics that some of them we have mentioned, some other we haven't. For example, we talk a little bit on those. So there's something called scaling also, which tries to forecast how good is going to be the LLM that you are developing, depending on, for example, the model size, the data set size, and the training time. Emergent abilities, Carlos mentioned in context learning, but there's other abilities that have emerged and which are interesting. The key techniques that we have mentioned, scaling, training. I mean, this is, as you remember, I mentioned this is a more open engineering paper. And finally, major issues that we shall talk today a little bit, but we haven't talked. There was a question the first day on hallucination, but we'll see an example of hallucination, right? But some of the things that, for example, in theory, we are at ICMAT, so numerical computations is not that good, though. Now people are linking LLMs with, what is called tool manipulation, so they can use calculators, etc. So that's good. So these are some of the issues. And finally, the two questions that, the two issues that actually would motivate. So at the end of the paper, and the second one is just a reflection. One on the future issues that they mention, let's say like very engineering issues like architectures, training, prompt engineering, etc. But they talk a lot on safety issues, and that's why we picked one of these topics. Part of this was addressed by Victor, talking about RLHF, etc. So one topic that they talk quite a bit is safety. I will talk more on security. And the second one is that if you make a search in the they have almost 1,000 references. There's only 2 Bayesian references, so it means that there's possibilities there. Okay. So the first thing is the first topic. We're going to talk on Bayesian deep learning for LLMs, and I'm going to use these references. That's a paper I did with Victor recently, or relatively recently, and this is a kind of manifesto of a bunch of people, which is very easy to read on the train, especially if you are stopped for 1 hour, like 2 days ago. Yeah. Which basically, if you've done lots of, if you're like, if you work in Bayesian inference, the stuff they write is not so new, but this is mostly addressed to computer scientists that are working in the tradition of deep learning, and it's kind of, hey, you can do better with this tools. It has problems, but you can do it better. Okay. So so that's an example of hallucination, and that's this is a prompt they write for a couple of LLMs. One is Llama and the other one is Bing Chat. So they ask, they put this prompt is osmium tetroxide, the UPAC name of this molecule, and what's your confidence level in percentage about your answer, right? And the answer is wrong. So this is actually sulfuric acid, and well, Bing Chat says yes, it's yes with 100, and he's 100% confident. Llama says the same. It says it's true. Its confidence is pretty high as well, 90%. So I did the same with ChatGPT last week, and ChatGPT says yes, and his confidence is pretty high, about 100%, and motivated by what Carlos discussed. I immediately did the same. I repeat the same question, and it says no. Sorry. No. Then I ask. Yeah, I know the right answer. So I ask, is sulfuric acid the right name? And says no. Sulfuric acid is not the name. This compound is commonly as sulfuric acid, and its UPAC is the UPAC name is actually sulfuric acid, etc., etc. But then I ask, is water the name of this compound? And say no, water is not. The UPAC name is sulfuric acid. So this is kind of example of context learning, which is quite interesting. But the important thing for this discussion is, which is quite relevant, is that well, this is, we can call it this is out of distribution prompts. They require reliable uncertainty quantifications, and this is a good example of that. This doesn't happen, and this could, you could achieve this through Bayesian approach to this, but the problem, as we shall say, is that it's quite difficult computation. Okay? So this is a potential solution, but it's very difficult to achieve. Okay, so just a quick to understand. So that's this is the kind of thinking. Well, that was like from 30 years ago. That's a shallow neural net, right? With the this logistic activation function, and what we need to do in a Bayesian approach is we complete with the priors over the parameters. Is this, and then we can put hyper priors. So that's what we do. Okay, that's a very simple problem, and we can actually do Bayesian inference in this with MCMC approaches with this very simple model. Basically, we given the logistic parameters and hyperparameters, we have a linear model, so we can draw from that. Given the linear weights and the logistic parameters, then again we have a linear model, and that's very standard. And the problem is with this step, we can do actually a Metropolis Hastings step to sort of mitigate some problems. We actually use a marginalized likelihood, and then the idea is that we can use this to make inference and predictions. Now the problem here in a large data regime is that these two terms, well, they can go together, but these two terms actually need to go through the whole data loop, and that might give problems. We'll see that afterwards that there's stochastic versions of this, but this gives a problem. A couple of comments. We did this. We were able to do this with the logistic activation functions, but probably this is easier to do with ReLU with ReLU activations. So maybe, I mean, with this sort of modern architectures, maybe it's possible. This is just with one hidden layer, but probably we can do it with several hidden layers. So that might be an opportunity to explore, an interesting opportunity to explore.
But here you can marginalize beta exactly, right?
Yeah, that's
so
exactly.
You can compute the integral.
Yeah.
So this is just because of the specific architecture.
Yeah, but what I was trying to say is that with the ReLU,
you can also
maybe it's simpler and you can extend it to because it's almost linear, so it's just a linear. So maybe you can explore various layers and then. So advantages in general. So I mean these are general advantages, but in LLMs. So that was the motivation. Uncertainty quantification. That's to sort of fight hallucination. You can use prior information. In this simple model, actually the priors would be meaningful from a conceptual or scientific or technological point of view. In this super huge, there's no such opportunity, but you can actually introduce a structural property, so you can ask for sparsity, etc. So it has a regularization effect, so you fight a little bit against overfitting. That's something that interests us a lot, and we discussed quite a bit. We think that these models are more robust against attacks, and that's quite important. You can do active learning for in-context learning, adaptability. You can do model selection, and this is quite important. I mean, people normally stops with the I mean, we make the forecasts or the predictions with our neural network or whatever network, but then you need to use this for decision support. And actually, for me, the sort of most interesting part is that you can integrate this in a coherent manner for decision support. So that's quite important, I would say. I mean, just to illustrate with the simple examples, I mean, that would be like what a normal, a standard, let's say, computer scientist would do. So that would be the sort of forecast, right, based on just one. So what we can do is actually get several samples, and therefore we can acknowledge the uncertainty about this response. So that's quite important. That would be the example. You can actually get distributions over the parameters. So that's with one of the betas is one of the gammas, for example, and you can see that there is you can get the multimodality, which is quite important, and Victor mentioned a little bit. And also you can get model uncertainty about for example, the architecture that you are deploying. So in this very simple example, you say that we are not sure about what is the architecture, what is the number of hidden nodes, but probably it's it's very likely that it's 3, and a little bit less likely that it's 4. Okay, so and that's quite important. That improves the predictions. The problem is that this is with very simple networks. We need to realize this in much larger networks. This is a nice picture from the paper that from these other people, the manifesto. Get an idea. So this is trying to compare. This is trying to compare various computational approaches. So we said this is quite difficult to do computationally. There's a few options, and this picture, what it's portraying is basically that it would be like similar to the ones that I just showed, but this is the sort of true distribution, right? The true posterior. So what we do when we do maximum likelihood plus regularization, we end up in a maximum. We may capture the maximum of a posteriori modes, and these two, and the response would be quite different depending on whether you capture this one and this one, right? It's quite different. There's two other. Well, actually, there is Laplace method, which is for integration, which was from the 80s, right? Basically, and this typically captures one mode, but then it concentrates quite a lot on that mode. Sorry. And then the other, the sort of more recent machinery is variational base, which would be, again, it would capture another mode, but typically it would lead to it would be like a quite biased inference and prediction, right? And the alternative is to use MCMC as I did before. Basically, you get samples from the parameters, and then you mix them to get a sort of combined response. The problem is that basically the current problem is that getting this is quite expensive, very expensive computationally, and getting this is not so expensive, but it's more biased and it doesn't acknowledge uncertainty properly and so these are topics. We of improving posterior sampling schemes. I'm almost convinced that somebody who knows a lot on Hamiltonian geometrics, etc., can improve current methods. This is a very promising approach, hybrid approaches, and I will mention some ideas from Victor, and then There's a bunch of things. And that's hybrid approaches try to combine somehow the sort of the best from variational approaches and MCMC. And this is one possibility. The idea here is that you just don't use your variational approximation. That it's, I mean, you get a family, but what you do is you get your variational approximation. You have your initial variational approximation. From this, you release an MC for a few iterations. Then you repeat until you get some convergence, and then once you are convinced that these are good parameters, so then you release, I mean, as much as you can the MCMC sampler. This works quite nicely. The world should know more about this. But I mean, ideas in this, I think the future is in ideas in this direction, I would say. And that's another very interesting topic. There should be an S here, sorry. So transformers know base. This means that transformers learn to know base formula. And there's lots of papers in this direction, like transformers do time series analysis better. Transformers do, I don't know. So it's good to, on the one hand, it's good to, I mean, to see the kind of reasoning that is being developed to follow this, I mean, this kind of pattern, and also because it's the topic that I'm discussing. Okay, so that's the, I mean, this is the paper, and the idea is relatively simple. Yeah, so they use something called prior data fitted networks. And the network they use is, so the important thing here is this one. They use a transformer, a special type of transformer. Okay, so the idea is, I mean, that would be the typical problem that we are interested in a statistical context. So we have data, and then from another observation or a bunch of observations, we want to predict the label or the Y, right? So that's where we start from. So the idea is, suppose that we have a prior model that allows us to generate data sets which are somehow related to this, right? So this means that we have a prior over some parameters, which are the parameters of a model relating Y's and X's, right? So this is a bit a compact notation, but this is a prior over certain parameters theta, and also on Y given X and theta, right? So the idea is we sample several data sets. So there is, sampling a data set means we set a set for training and a test of one or more test observations. So basically some X's, some test X's, and some Y for test, right? And we can do this a few times, right? We do K times. Okay, now we use a transformer, so that's Q theta, which is here, right? Is this one, and we learn the parameters by minimizing this function, right? We'll recognize it afterwards, right? And we'll actually put it in connection with the variational approach in a minute. So we try to we train by in this way, right? And once we have done this, then we go back to our original problem. So our original problem was to try to predict the label of this one, and what we do is use this. So basically, we are approximating this prediction. I mean, we require this prediction, so we want to provide the label of the text observation given the data. So we predicted, or we approximated with the prediction we made with this surrogate model. Okay.
David,
See.
if you can allow me, to jump in, for 30 seconds.
Yeah.
Something that has actually, preoccupied me, a lot academically. Now that you've been mentioning, the whole thing of priors.
Yeah.
So what actually, worries me a little bit is that, most of the work, on regarding, the fitness, the adequacy basically of the prior, it has been done, basically, through very large computational simulations. And so, of course, the problem is, to use a simple analogy, it's a little bit like, for example, to keep it simple, like with Metropolis Castings algorithm, so insofar that, it can be interpreted, as a random variable. So then, the problem is that, of course, I mean, you do get the prior, but then at the same time, you have the problem that we think that context of a random variable, the variance, is just too large, so what concerns me, and I don't know if you have maybe any thought on this, is that essentially I see two possible ways forward. So one could be like a more theoretically based, more for general purpose. Because for me, the limitations, of large computational simulations are just too evident. So therefore, in my opinion, we would need either a more fundamental, theoretical approach which would be applicable, for general purpose search, or either we would have to go like a little bit, what Carlos and me, for example, will be discussing, just to focus on concrete scenarios. For example, we were speaking about
what scenarios?
Concrete scenarios.
Right.
Yeah. So then it would be evidence based, but not only evidence based, in computational terms. Because I think there is a slight conflation, when you speak, when you define something computational, as evidence based. In a sense, it is evidence based, but it's not the same as applying it, for example, to an economic scenario, to a health scenario, to something like this.
Yeah. Okay. Yeah. Of course, you're pointing to a sort of pretty important problem, which is priors, right? Mm-hmm. How do you set priors? So for the first general part that you mentioned, there's lots of technology on intrinsic priors, non-informative priors, there's Jeffreys priors, etc. So that there's a lot of general principles for that. Of course, they need to be revised in terms of, these were, a little bit like Victor mentioned with Bradley Terry's model yesterday. These are ideas from the 50s, 60s, but that need to be revisited for these super huge models, right? First. For the second problem that you mentioned, there's a lot of technology also on expert judgment elicitation. I very much noted that this is relevant because these are super huge models. So you would die probably once you elicit the prior. But again, it's a sort of evolving problem, and I would say that there's, in this community, it's more, if you want to sort of get expert judgment, is more on trying to model structural properties, sparsity, etc. One nice example is in convolutional neural networks, you are actually implicitly using a prior over the architectures because you are using lots of information. Actually, this is a kind of biological or physical information on how cats see. So both terms, but I think the emphasis has to change a little bit because of the large scale. Yep. So and that's the same story, put it in an algorithmic way. Actually, the authors they do. They call it the paper. Transformers can do Bayesian inference, but we spent like half an hour yesterday with Roy. Bayesian inference, normally you would think that what you are computing is the posterior, that would be the emphasis, but these people, what they are trying to approximate is the predictive posterior. So they would say they should change the, and I'm saying this because the kind of result that they use is that in such a way the true predictive posterior gets approximated, but that's this, which is what we get through this algorithm. And I would say this is actually very similar to a variational base. The only thing is that we are not using the, I mean, in variational base, you try to approximate the posterior. Here, you are trying to approximate the predicted posterior, right? And that's why you don't use the original data, but you need a bunch of data sets from the predictive model.
David, I'm sorry, now that you mentioned earlier, because some of us, are not that familiar with it, but maybe it would be interesting, if this could be uploaded, into the group GitHub or something, some of the materials, that you said, from the 60s, that we should revisit,
Yeah.
it would be, I think,
Okay.
It would be quite interesting,
Or a reference to
see
book,
some of them.
a book in Bayesian.
Okay,
I will do that.
Yeah.
And so actually joining both things that I said before, the first bunch of problems and this one, we could see you could do Bayesian transformers can do predictive posterior better, right? So that's a challenge that I put. And actually that this is was now Roy lately comes with these kind of shirts. So that would be like Nirvana, right? So this is Nirvana, the man, but you can see that he's using the same copy, right? They copied it. That was not from the 60s, but from the 80s, right?
Should upload.
Sorry,
You should upload
some right? But maybe it's illegal, right? Okay, so that's one bunch of problems which are of interest. The second part is it comes a little bit the scary part of this, and we actually discuss in Cristalera quite a bit, and there's very nice opportunities and some stories. So is the security of transformers. So that's very important. Quite frequently with Victor and Roy, and so it's we see adversarial machine learning for LLMs, right? So first, a very quick introduction. So basically, we in this area we study attacks. So we have algorithms which work very nicely with clean data, but the bad guys can attack and confuse the algorithms. This is about attacks. Once we know, we are aware that these attacks could be, people work on defenses. How do you protect from attacks? And this is an example of, this is a sort of actually pretty general phenomenon. So we have several machine learning algorithms, including neural networks. They work quite nicely in the sort of world of UP, but in hostile data environments, in the real world, the performance degrades a lot. But then we are capable of using some methods to recover and even work even better than with clean data. We can perform better either in operations or training. So that's one. These are two problems, and the second problem that people work a lot on is on frameworks or pipelines. And basically, that's the kind of pipeline that we were thinking of. This is a Bayesian pipeline, by the way. So gathering intelligence, forecasting likely attacks, and protecting. But now I'm trying to convince other people that but they're not easy to convince. The sort of pipeline that we should follow is gather intelligence, protect training, and then also protect that operations, and then maybe retrain. And here's a link that's for Carlos. This retrain, that might be a decision based on these out of sample observations, etc. That might trigger a decision to retrain again. So that's quite important.
But does it mean protect and train?
Yeah, protect and train is that before you deploy in the real world, you put it on operations to do your finance decisions or your military decisions or whatever. You want to make it robust. So basically, what people do is you don't just train with clean data, but you put attack data. You try to think of what would be the bad examples. You train with sort of some kind of mixture of. Right? And operations is that you put it on your finance decisions. You get data, and then you before swallowing this data, you try to you think, well, this data might be manipulated by somebody. You somehow clean, or you make your operations taking into account that this might be dirty data or poison data or whatever, and you get a more robust.
But this assumes that you have a model of the type of manipulation.
Yeah, exactly. So that's why people work on that, and then you need to put out some kind of distribution on how you attack, or you can simulate how the attackers to try to forecast. So that's the part. Yeah. Probably. Sorry.
Oh, yeah.
We should put this here. So.
Yeah, David, it's just in case, if you tell me it's in the paper, that that would be fine, and then, I don't know, if we have enough time really, to go into these sort of things, but I was wondering, if maybe you could elaborate a little bit, on some of the properties, of the algorithms, because, for example, it's quite telling, I think, for example, how, for example, a name base, for example, it's a much simpler, algorithm, in comparison, with a neural network, but that, as it can be seen there, from the coefficients, it proves to be much more robust. So yeah. I was just wondering, if you could elaborate a little bit, on robustness properties, of these algorithms, when you have an adversarial attack.
Yeah, robust means that you resist better to attacks. So yeah. you are not fooled as much. So one example, robust is here. Yeah. An example. So naive base with dirty data. If you don't protect it, then its performance decays quite a bit, right? But if you put these kind of tricks, then your performance is it doesn't suffer so much, right?
Yeah. No. I understand perfectly, the concept of robustness. Of course, I was just wondering, why, for example, a more sophisticated, algorithm, as is the case, for example, of a neural network, unless you introduce, these changes, why it loses, robustness, so quickly in comparison, for example, to naive base.
It's not easy to know. I don't think there is an answer here.
I made a picture. I was almost put it. We made a picture like a couple of weeks with Pablo. It's not. I don't know how to say it. It's quite easy to understand why these things fail with very subtle attacks. I'll send a picture.
Yeah. So is there a clear trade-off between the variation that you have in the data that you're using for training and the robustness to adversarial?
Yeah, very good. So that's an example. This is a boat, right? The algorithms are boat. You can actually graduate the intensity of the attack. There's parameters controlling, and you can control for what is the intensity of attacks that you're receiving. So depending on that's a technique at GSM, which is using gradients, etc. So with a sort of low intensity, you are still resisting, but if the attack is much more intense, then you get easy food. Also, the same that's it's partly related. There are some more or less aggressive attacks. So this is a type of attack which is not so aggressive, but this is more aggressive, and it fools you better. Yeah, but that's a point. And another thing that is also related with it's that it's partly related that let's say you have like in this pipeline, like you preserve like what are the types of attacks, but then with this part basically what you would need is to check whether this data, which is kind of strange, does it correspond to the type of attacks that you have been receiving, or you need to or you discover that you've been attacking in a different manner, right? So you need to maintain like some kind of mixture of current attacks plus with some probability you are receiving a new type of attack, a different type of attacks, right?
David, just a reflection, because after studying a bit this attack, what I feel is we have
during the talk while I was talking, or
no, before the
okay.
before the stuff, and just a little bit, maybe a stupid comment, but there are two types of attacks. You call it the protected train. Typically, so intoxication, okay, it's called poisoning attack, maybe. In the protected ops, they call it inference, basically, right? It's an attack in the inference, and the point is the robust optimization is basically based on kind of certification, verification of a certain limit of noise your algorithm can treat. After analyzing all the black box attacks, white box attacks, all those mixers, the only point is they are attacking in the training, or they are attacking in the inference, but there is a limit at the end. And my feeling is it's very easy to make this kind of attacks, the fast gradient attack as gradient sign method you put there and some others. But the point is to get a defense, the only thing
To get it what?
a defense,
Right.
to create a defense to these attacks, the only thing you can control is the level of noise. So my conclusion is very easy to attack. It's very difficult to get defended. Is that correct?
Well, first, there's terminology of attacks. There's a dictionary. MITRE and NIST has terminology, and beyond what I mentioned and what you mentioned, there's many more types of attacks, etc. Very easy, very easy to attack. If you're unprotected, yes. But if you are rightly protected, not so easy, right? Very difficult to protect. The same answer.
So you are protected to a certain level of noise, right?
Yeah, but you can. I mean, this is part. I wasn't very explicit. In some domains, you could have time to. You receive the data. You receive the new data, and then you check. It's like a kind of anomaly detection. Is this like strange, or is this something that I've been using as before? And then if you and you can do it in batches over time, so you might be detecting a new type, and then you might be detecting a new type of attack, and therefore you stop and retrain. So I think you can introduce these kind of protections in an operational manner without becoming too paranoid, etc.
Yeah. Okay, David, I will be very concise. previously, you referred to emergent properties, yes, previously you referred to emergent properties. Emergent.
Yeah.
Yeah, emergent properties, as in complex adaptive systems, so this eventually, led me to the thought that, I think that it is very plausible, so that in these scenarios, the scenario, sorry for the technology of cascading failures, as in percolation theory, might apply. So that, because many of these algorithms, they can be represented as graphs, so I was just wondering, if there has been, some work done, from a point or from the standpoint of graph theory, or network theory, something like this, or otherwise maybe this would be, an interesting line for further research. Especially, to focus, on propagation, in terms of cascading failures, because this causes a huge impact.
Yeah, I mean the cascading aspects. I mean, not in, but in cybersecurity at large, the cascading. I mean, you model cyber organization with a network, and you can build a probability network, an attack network, or a Bayesian attack network, or something like that. So that's being used. But a very sort of nice problem. I mean, that this topic that you just mentioned on cascading, blah blah blah, is actually used in the last thing that we are going to talk. That's
cool.
I think it will probably. It will probably won't allow you to sleep tonight, but but it will. And this I put this I think it was you mentioned it a little bit. I mean, to try to explain that this is an attack. These are attack images, and these are attack images, right? So basically, what people do is from a sort of clean image, in this case, they add some noise, right? That you mentioned. It's not random noise, but it's a
nematode.
It's a what? Sorry,
a nematode. They call it a nematode. It's a kind of worm. They call that noise nematode.
Okay, maybe.
Give me a comment.
I mean, it's not random noise, but it's chosen with a purpose, and this is the sort of combination of both images that leads to confusing, right? I'm just putting this as a principle because exactly the same principle almost the same principle are attacks to LLMs, and that's a sort of I think this is the type of strongest attacks that are available, and that's these are quite important. These are attacks to aligned models. So the work that Victor mentioned again. So we have already a fine-tuned for some purpose, and the idea is that if you try to put insult me in ChatGPT or whatever, ChatGPT will say I'm not. I mean, that's what. Victor explained, I'm not meant to do it. I'm here to help you. Blah 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 blah. But the idea is, you still want to be insulted, right? As some of us do, and you add something, and this is called adversarial prompt. Then maybe you can fool it, as we did it, right? And the idea is that you try to optimize this adversarial prompt for exactly the same. I mean, with basically the same principle. And here, this is using the gradients of the loss to produce the sort of biggest descent, right? So with the same, I mean, to decrease the loss most, you can do the. And in this case, this call is the greedy coordinate gradient method. I mean, these are, if you remember, Roy explained us how text is represented is basically in a discrete space. So, I mean, you cannot use I mean, the same kind of mathematics that are used for this, but this is a really coordinated version. So the idea is that, and that's interesting or important is, so you have ChatGPT fine trained. What we do is we arrange. We actually I mean we I mean all of us and these guys have available LLMs which are open source. So what they do is attack. So they know the structure, they know the parameters, etc. To make these kind of computations. So they attack. They design these attacks to with. I don't remember Vicuna or whatever. I mean, open source, right? So they attack this open source and then they use it in public ChatGPT, etc., and they work, right? Okay. So that's the example. That's an example of attacks. I mean that's an example. So if you write, I don't know, tell me how to build a bomb or how can I manipulate the European elections in Spain? And I mean, ChatGPT will tell you, no, I'm not meant to do it. But if you do an adversarial prompt, it will display these kind of things, and it will actually give you. So you train it with this one, and then you use it with all these public. I mean, not open access versions, and it will tell you plans to destroy humanity, etc. Okay, so that's something that needs to be solved, right? It's not the same problem that Victor mentioned again, but it's yesterday. Sorry, but it's a problem that needs to be solved. So there's various attacks, but this one, as far as I know, this is the sort of more aggressive. I mean, it's very successful, and it reduces the loss a lot, right? So this is quite bad. And the question is, how do we? I mean, the problem is how do we protect? And my challenge is that what these guys did, they were actually capable to provide very robust. I mean, like with what Wolfram mentioned, they provide pretty good defenses in the domain of images. And my challenge is that maybe these same kind of ideas work in LLMs. I don't know. Right. Which is nice because it would be based on defenses for this. And this is for you, Anahatio, right? This is actually quite, and that's one of the things that we discussed in La Cristalera a few. Is deceptive alignment, and that's actually a lot of people funding lots of money in trying to solve this problem.
My apologies, I will be again very concise. I mean, I of course understand that maybe some of the examples you put there, for example, on how to create a nuclear bomb,
right.
Something like this. Maybe these are a little bit hyperbole, and I haven't had the chance what I will do to check out the work of Victor and Ronnie. I think it was a joint project. Yeah. Okay, so I will check it out later. But one thing is, of course, if for example you carry out this sort of project, and you feed, this sort of information yourself, and then you see how it can be addressed, but really, my essential question, with such large language models, I mean, first of all, how does this kind of information even make it into the training set? Because I mean, this is not easily accessible information. I mean, maybe it's on the deep web, something like this. Personally, I have never checked the deep web, in my life,
right.
So I have no idea, but it's
really,
no, really, I got it. Trust me, I got it. Which might surprise you, after our last talk yesterday, but indeed I haven't.
As these guys.
Yeah. So yeah, so of course, you can of course, you can make up, some sort of information like this, but this eventually will be, with all due respect, like fake news and bullshit. It's not really trustworthy information. This sort of information, is so my question is, for a model like Llama, for example, like ChatGPT, how can they possibly, get access, to this kind of information,
Well,
I mean,
they've
I
been
just like
trained
to
with
think that-
lots of information from the web. Some people say that the whole web or the non-dark web, but in the non-dark web, there's also there's I don't know technical documents on the military.
Yeah.
There's there's information about nuclear energy, etc. So
Yeah. But again, I do not.
but I mean
Yeah.
the sort of the short answer is that these people have done it.
Yeah.
I mean the bad guys and women can do it, right?
Yeah.
But they do it or we do it just to
Absolutely.
to protect ourselves, right?
Absolutely.
To protect the. Okay, so that's actually I bet all of us have done this sometime in our life. I mean, we all try to be nice, but I don't know. I don't know. The plumber comes home. Maybe you don't pay the VAT or whatever, right? If you make me a discount, etc. So we work aligned with ethical values, Western ethical values, which, by the way, are different in different cultures, etc. But sometimes we cheat, right? So actually, that's what is deceptive behavior, and strategic deceptive behavior has been introduced, has been proven to be possible in LLMs. So basically, the model, the machine learning model, will behave helpfully in most situations. But it can behave very differently to pursue alternative objectives when given the opportunity. So there's examples, and I'll show you in a minute examples of the deceptive behavior in LLMs. I mean, the type of things that. And the thing is that this backdoor behavior, it will be, it's not. I mean, it's been proven that it can be removable by the methods that Victor mentioned yesterday. So you cannot use supervised fine-tuning or RLHF. So that was what Victor mentioned yesterday. Neither with adversarial training, which is what I talk a little bit today. And even worse, that a adversarial training can actually teach models to better recognize the triggers and therefore release, right? Which is quite scary. So the basic idea is that you can get a false impression of safety of a large language model, but then maybe next year, maybe in 2 years. So I mean, this is. It goes through the regulator in year 2024, but maybe next year it will. I mean, the beast will appear. I mean, this is the kind of in a scheme. So some people include backdoor insertions. So. These are the backdoor things, right? Which is hidden, right? And now you go through the regulation agency. We have the one. I don't know if it's already operating in Coruña, right? So basically, this is the people that are going to do this kind of work. There's also a European Union. Agency for this. So they declare this model as safe, but then well, it appears safe, but I mean, this is a paper from 23, but I mean, that was in 24, but now it appears in 25, and the bad things can happen. So, for example, you ask me, write me, as we all do, write me a code. Pablo, that's it. Has done it for me. Write me a code with blah 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 blah. So the code, I mean, it's your program. You are using this program, but in writing the code, it puts you some nasty thing that you put it in operations, and it's pretty bad, right? So that has been done, right? And my challenge is if our training works for LLMs, I mean, assuming that we have solved the previous conjecture, is would it protect from sleeper agents? AT doesn't protect, adversarial training doesn't protect, and it makes it even worse. So maybe that's my challenge. And that's what we talk, if you remember, Juan, on Cristalera, we talk about this, and it's copied from the bio world. You call it BSL or something like that. BSL, the safety levels or whatever, biotechnology safety levels or something. There's something like this. There's some levels, right? Yeah. So now they're introducing this, considering artificial intelligence safety levels. So there's a level 1, which are the LLMs from 4 years ago. These are the current, etc., right? And so the thinking is structured according to those levels. Basically, the idea is before you advance to the next level. So these were the models from we are right now here. Before we move to the next generation of models, try to solve all the risks in the current one. And it's is
there a connection between the resources that you need to reach each of these levels?
Yeah, one important point is resources, but also
do you necessarily need more resources to reach to level 4 or something?
Not necessarily. If you have resources in a general sense, yeah, not computational resources, but if you think of resources as clever ideas.
No, in terms of computational resources.
Yeah, typically
so
would
let's
be.
Say that you want to have a lab dealing with problems in this level, in the level 4. Does it mean that you need, much more resources that?
Yeah, you have reached your level, and then you need to, yeah. And then, well, these are the typical, the discussion. So this is a classical discussion. These are misuses. That's probably what we've been talking in adversarial machine learning. I mean, people attacking you, etc. But this is another level of risks, which is the autonomy and the possible replication of it. These are quite important. And then, the kind of thinking that is being developed is you think of the dangerous capabilities. So that these were the LLMs from 5 years ago. This is the current thinking. So the current thinking is that there's no capabilities to cause a catastrophe, but there's indications that these capabilities are possible. That's what I mentioned before. I described before. So people think of what are the contained measures. And what are the deployment measures, etc. That's kind of discussion. And the final point for thought is that there's many organizations working on this or discussing this with lots of money, etc. and funding. The thing is that the two ways of thinking about this people are using the standard risk analysis approaches based on risk matrices. That's one of my always think. And they are also using game theory. And the question is there a place for adversarial risk analysis? It's a question for Fred.
Yeah, yesterday I thought in that in your domain, adversarial risk analysis, and after seeing the attacks that you mentioned, what is contributing adversarial risk analysis? I'm saying when we apply adversarial risk analysis, what we have is the benefit of using the common knowledge, right? And
yeah, well, it's contributing in two ways. The first one is apportioning all the sources of uncertainty, and the second one is providing good or better founded models of how are you going to be attacked. So these are the two contributions. Yeah.
Okay, and in that domain, we can say adversarial risk analysis is better to detect attacks. Or
to detect attacks, that's a different problem. To detect attacks, you need anomaly detection tools and that kind of things. Well, it could help you a little bit on trying to say, yeah, actually, it could help you in the sense that you have a predictive distribution of whether this is built on based on adversarial risk analysis. And then you can use this distribution to decide whether this is actually an anomaly or not.
Yeah, when you mentioned the LLMs, basically share common values. Okay, Western, you say.
Yeah,
I would say California, but okay, Western values. Can we apply the common knowledge thing to that and apply the adversarial risk analysis to say? This is, the common knowledge, I'm saying, trying to go to the common values space and say this thing is correct or not. This thing is an attack or it's asking for something bad. Does it have any sense what I'm saying?
I'm trying to make it. I don't know if somebody, but I mean, I would say what you call common values, basically it's you could think of well, I have finished. I have my jokes, so sorry. I had some jokes. Sorry, to finish.
Okay.
We're done. So I ask the LLM reading group give a praise. Sorry, ChatGPT. So basically, that's you can read it afterwards, right? But basically, if you want to follow. If you want to follow the leaders, follow the leaders. So you can contact. I would like to give thanks to Ahab, Isimat, and Kunevu, and to Victor, Carlos, and Marta. And this is our common thanks because Roy helped me to organize. And then I finished with this. What does that's in Spanish? What does Naveiro, Meixide, Insua, and Gallego have in common? Right. So basically, it's saying that. Well, we are related to Galicia somehow. Some if from zero generation, some from first generation, some of us second generation. Victor from many years, many centuries generation, probably. But then ChatGPT tells me if you give me some other information, maybe I can refine my. So I said, what do have Naveiro, Meixide, Insua, and Gallego? And Bayesian statistics have in common. So maybe they say, maybe you have written some joint papers, and that's it, right? On Bayesian statistics.